Assalamu alaikum. Hi students, it is me Tavinda Yasin, your teacher for classical mechanics for the course code BHY509 for the semester BS 5th. Now we are going to start the classical mechanics, another chapter that is very important in the mechanics of the uh, different bodies, and that is the kinematics of rigid body. We are going to consider a rigid body and describe many properties and phenomena associated with the rigid body, of its translation and rotation. Now starting with that, we will move to the contents. We're going to study about the kinetic energy of a rigid body with one point fixed, define inertia tensor, and then we're going to define tensor, and then with the after tensors we're going to discuss the inertia tensor and the moment of inertia relation, and in the last we have some of the references. Now we're going to start with the kinetic energy of a rigid body with one point fixed. The theorem for that is find the kinetic energy of a rigid body rotating about a fixed point of the body when the moments and the products of inertia of the body relative to the set of axes through fixed point are known. That is the theorem that we have to find the kinetic energy of rigid body that is rotating about a fixed point of a body when the moments and product of inertia of the body relative to the set of axes through the fixed point are known. We can consider a rotating body and a center of axis along which a body is rotating, and that a center of axis is a fixed point. Now we're going to start the proof. So we're going to consider a rigid body composed of n number of particles having mass mi and rotating with the instantaneous angular velocity omega. You know that angular velocity is designated by omega sign. If one of the points of the rigid body is fixed, then the translational rotation is absent and the body rotates about an axis passes through the fixed point. That means if any point on the rigid body is fixed, then the body cannot translate, but it will try to rotate along that fixed point. Then rotational velocity will be equal to vi is equal to omega, uh, that is the angular velocity omega cross ri, that is equation number 1. We know that the kinetic energy of the body is given by for the sum of the system of particles, the kinetic energy will be T, capital T is equal to 1 by 2 summation I mivi squared, that is the equation number 2. Using equation 1 and 2, capital we are going to substitute the value of equation 1, that is capital T is equal to 1 by 2 summation I mivi into omega. We're going to separate a vi from that, and that will be vi dot vi. So we're going to substitute one value, that is omega cross ri. On using the vector identity as there is the vector triple product, so a dot b cross c is equal to b dot c cross a. So from that we write the expression for the kinetic energy, that will become capital T is equal to 1 over 2 summation I mi omega into ri cross vi, that is the vector triple product applied here. So from here 1 over 2 omega is written out of the summation, then the product will become summation I ri cross mivi. As mass is constant, so it can be taken inside the cross product of the bracket, then it will become mivi. So that term is the momentum, so at that place we can write 1 by 2 omega summation I ri cross pi, that shows the rotational motion of the object. So that r cross p or the ri cross pi shows that that is the angular momentum. So that will become t is equal to 1 over 2 omega dot l, that is equation 3. Here you can see that it is the product of angular velocity and angular momentum. So where l is equal to summation I ri cross pi, the whole term is equal to capital L. Now moving next, from the equation 3 we will work out It is the total angular momentum. Now to express the kinetic energy in terms of moment of inertia and the product of inertia, we know the angular momentum of the rigid body is given by L is equal to I double dot. That sign is for the angular inertia of the whole body. So L is equal to I double dot omega. That is equation number 4, where I double dot is the moment of inertia in the tensor form. So that is given by that tensor is the you can say that it is a inertia of the whole body, and in a matrix form. So that is written as I double dot is equal to matrix Ix, Ixx, Ixy, Ixz, Iyx, Iyy, Iyz, Iz, all the components in the matrix form Izz, Izy, Izz. That is the question number 5, and that is the tensor form of the inertia. Hence, equation 3 becomes capital T is equal to 1 over 2 omega I double dot into omega. So in the place we wrote this, if the components of the angular, and giving that equation number 6, if the component of the angular velocity omega and the angular momentum vector L are, if we write in the component form, that is omega is equal to omega x I cap plus omega y j cap plus omega z k cap, and L is equal to lx I cap plus ly j cap plus lz k cap, and that is the both of the equations are given equation number 7. Then we write the equation 4 as, from equation 4 can be written as, in the matrix form, that is Lx, Ly, Lz is in a column, that is equal to the tensor form of inertia, and in the column we write omega x, omega y, all the components, and by this we are going to solve and expand the matrix. So Lx I cap plus Ly j cap plus Lz k cap, that is equal to, we are going to take the I cap, and that will become Ix x omega x plus Ixy omega y plus Ixz omega z plus j cap, that will be equal to Iyx omega x, Iyy omega y plus Iyz omega z plus, and k cap will be equal to Izx omega x and plus Izy omega y and Izz into omega z. Hence from equation 6 we can say that hence equation 6 becomes, then we, after substituting that value, we have t is equal to 1 over 2, we are going to write the value of omega, that is omega x I cap plus omega y j cap plus omega z k cap, and substituting the value of L, that is the component value, that we're going to substitute that whole value and on that place. So this equation becomes, by the dot product, you know that I dot I and j dot j and k dot k is 1, and except that the I dot j, j dot k, k dot I, j dot I, and that are all 0. So it means that Ix x is square and 1 by 2 is common. Similarly, all the components will be written, and that will become equation 8, that is t is equal to 1 by 2 Ix omega x square. We're going to multiply that I cap with that I cap whole term, that is Ixx omega x square plus Ixx omega x square plus Iyy omega y square plus Izz omega z square. That is the first value multiplied. Then we're going to multiply and add. That will become 2xy. That is the complete form. You have to solve the one step here. The only one step is missing here. You can solve easily. by multiplying the first term of I dot I cap with the omega x, the second term of whole j cap with the j cap value, and the k cap value with the whole k cap value, and expand and then add and subtract. We will get these values 3 2i xy omega x omega y plus 2i yz omega z y omega z plus 2i zx omega z and omega x. That will give the equation number 8. Now, if the body rotates about the z-axis with the angular velocity omega, we have omega x, omega y, omega z that is equal to 0. In this equation 8 becomes, and from the previous equation 8 that becomes, if the z-axis velocity is 0, then all the components of x, y and z will become 0. So only capital T is equal to 1 over 2 I omega square will be remained, and that is the equation number 9, where I is the moment of inertia of the body about the z-axis. Now we are going to define what is inertia tensor, IJK summation convention, and from that we are going to write the angular momentum Lj is equal to IJK, that is the tensor form of inertia into omega k. IJK is also called the moment of inertia coefficients.
काइनेटिक एनर्जी ऑफ अ रिजिड बॉडी और रोटेशनल मोशन में हम देख रहे हैं ये। सो फर्स्ट में देखते हैं कंसिडर अ रिजिड बॉडी। अगर आपने ये इससे पहले आपने एंगुलर मोमेंटम वाली वीडियो नहीं देखी है तो पहले वाली देख लीजिए। सो हम स्टार्ट करते हैं। कंसिडर अ रिजिड बॉडी रोटेटिंग अबाउट एन एक्सिस पासिंग थ्रू अ फिक्स पॉइंट in it with angular velocity omega, a particle of mass mi and distance ri, velocity is vi given by कुछ नहीं है, रिजिड बॉडी है हमारी। एक फिक्स पॉइंट के ओर से ये यहाँ पर कोई पार्टिकल होगा, एक ओमेगा से ये मूव कर रहा है। आर आई इसकी डिस्टेंस होगी, एम आई इसका मास होगा और वी आई इसकी वेलोसिटी होगी। सो इसे हम इसका फॉर्मूला क्या होता है, v इज इक्वल टू ओमेगा इंटू आर। सो हम ये ith पार्टिकल के लिए कर रहे हैं, आई पार्टिकल के लिए कर रहे हैं। सो आई होगा और आई, क्योंकि ओमेगा तो सभी के लिए सेम ही होगा, क्योंकि एक एंगुलर वेलोसिटी ओमेगा से हो रहा है। सो हम इसे इक्वेशन नंबर 1 दे देते हैं। अब काइनेटिक एनर्जी ऑफ होल बॉडी, अगर अब इसकी काइनेटिक एनर्जी अगर हम किस तरह से, इसका फॉर्मूला क्या होता है, हाफ एम आई पार्टिकल कर रहे हैं, आई आ जाएगा वी आई स्क्वायर। सो ये कहाँ तक आएगा, आई 1 से n तक ये आ जाएगा। अब एक v की जगह ये रख लेते हैं, ये क्या आ जाएगा, ये हाफ बाहर कांस्टेंट टर्म है, आई इज इक्वल टू 1 to n। एक v को अलग से निकाल दिया है, ओमेगा क्रॉस आर आई, एक क्रॉस है ओमेगा क्रॉस आर आई डॉट एम आई वी आई, दूसरे वी आई को ऐसे ही रहने दिया है। इसको इक्वेशन नंबर 2 देते हैं। सो अब आप एक ये फार्मूला जानते हैं, ए क्रॉस बी इंटू सी, ये बहुत कॉमन फार्मूला है। इसका वैल्यू क्या आता है, ए का होता है ए डॉट बी क्रॉस सी, ए डॉट बी क्रॉस सी, इस फार्मूले का हम यूज़ करेंगे अब। सो क्या आ जाएगा तब, टी इज इक्वल टू हाफ आई इज इक्वल टू 1 to n, ओमेगा को ए ले रहे हैं हम, ओमेगा इंटू बाकी बी आर आई इंटू एम आई वी आई, ये हमारा थर्ड हो गया। सिंस ओमेगा इज सेम है, ओमेगा सेम है ऑल पार्टिकल्स के लिए, जितने भी पार्टिकल हैं हमारे ith पार्टिकल, उसके लिए ओमेगा सेम है। सो अगर ओमेगा सभी पार्टिकल्स के लिए सेम है तो ओमेगा को हम एक कांस्टेंट की तरह ट्रीट कर सकते हैं और ओमेगा इधर आ जाएगा। और ये जो बाकी फॉर्मूला बचा, सिग्मा आई इक्वल टू 1 to n आर आई क्रॉस एम आई वी आई, MIVI होता है PI। ये पिछले वीडियोस में हम डिस्कस कर चुके हैं, ये एंगुलर मोमेंटम का फॉर्मूला होता है। तो उम्मीद है आपको ये चीज़ें आती होंगी। इसे हम इक्वेशन नंबर 4 दे देंगे। सो वी नो दैट ये पिछले वीडियोस की काफ़ी चीज़ें इस वीडियोस में इस्तेमाल हो रही है, तो एक बार एंगुलर मोमेंटम ज़रूर देखें अगर इसे समझना है तो। एल का जो हमने फॉर्मूला निकाला था वो क्या निकाला था, आई ओमेगा एक्स। पहले मैं इसे लिख लेता हूँ, एक मिनट। सो ये मैं लिख चुका हूँ। अगर आप पिछला वीडियोस अच्छे से देख चुके होंगे तो ये फॉर्मूला आपको याद होगा। किस तरह से लिखा है ये, एम ओमेगा एक्स ओमेगा वाई ओमेगा जेड। पहले एक्स का एक्स के साथ, एक्स का ये वाई के साथ, फिर एक्स का ये जेड के साथ, फिर ऐसे ही एक्स इधर पर आएगा, वाई। इस तरह से आप कर सकते हैं। सो अब एल की वैल्यू को हम कहाँ रखेंगे, फ्रॉम इक्वेशन 4। ये बहुत इम्पोर्टेंट यहाँ पर मूव रहने वाला है हमारा। टी इज इक्वल टू, अगर हम यहाँ पर रखेंगे किस तरह से आएगा, फर्स्ट में हम ये वाले लिख लेते हैं, ओमेगा ओमेगा एक्स एक्स। अगर ओमेगा ओमेगा मल्टीप्लाई होंगे तो क्या आएगा, ओमेगा स्क्वायर आएगा। सो टी इज इक्वल टू क्या आएगा, हाफ ऑफ ओमेगा एक्स का स्क्वायर आई एक्स एक्स। इसी तरह से ओमेगा वाई का स्क्वायर आई वाई वाई। ये ओमेगा भी तो सभी का पार्ट होगा, एक्स का वाई का जेड का, तीनों डायरेक्शन में मूव कर रहा होगा। सो इसी तरह से ओमेगा जेड स्क्वायर आई जेड जेड प्लस, अब देखिए ध्यान से। सो पिछले वीडियो जो हम देख चुके हैं कि आई एक्स वाई आई वाई एक्स ये दोनों सेम होंगे, तो इन दोनों को सेम लिख लेते हैं, एक साथ लिख लेते हैं। सो ओमेगा एक्स ओमेगा वाई आई एक्स वाई, ओके। एंड इसी तरह से ओमेगा वाई एंड ओमेगा जेड, ये आ जाएगा आई वाई जेड प्लस ओमेगा जेड ओमेगा एक्स आई जेड एक्स। यहाँ पर इसके कोफिशिएंट में 2 आएगा, ये 2 से ये 2 कैंसिल हो जाएगा। सो इसे हम दे देते हैं क्वेश्चन नंबर, हम 4 तक पहुँचते 5, इसे क्वेश्चन दे देते हैं। अब इसे कॉम्पैक्ट फॉर्म में लिखेंगे। अब हम जो हमारा लास्ट मूव है, टी इज इक्वल टू क्या आ जाएगा, हाफ ऑफ सिग्मा बीटा ओमेगा अल्फ़ा, 2 ओमेगा हैं, ओमेगा बीटा आई अल्फ़ा बीटा। आई अल्फ़ा बीटा सभी में, ये इसकी कॉम्पैक्ट फॉर्म हो जाएगी। सो ये आपका है काइनेटिक एनर्जी फॉर रिजिड बॉडीज। सो इसमें एडिशनल एक और चीज़ है, अगर एक हम नया वेक्टर डिफाइन करें, ओमेगा रो इज इक्वल टू ओमेगा अपॉन रूट टू रूट 2t। सो फ्रॉम इक्वेशन 5 में जो जो जहाँ जहाँ पर ओमेगा है वहाँ पर आप रो को पुट कर सकते हैं। तो आप देख लीजिए, आई एक्स एक्स रो एक्स का स्क्वायर, आई वाई वाई रो वाई का स्क्वायर, आई जेड जेड रो जेड का स्क्वायर, आई 2 आ जाएगा दोबारा, आई एक्स वाई रो एक्स रो वाई, टू आई वाई टू आई वाई जेड रो वाई रो जेड, सब वही कर रहे हैं हम। टू आई जेड एक्स रो जेड डॉट रो एक्स। सो ये इक्वेशन क्या होती है, ये इक्वेशन होती है पॉइंट्स ऑफ इलिप्सॉइड ऑफ इनर्शिया। ये इक्वेशन होती है
Inertia tensor ij case mission convention Lj equivalent to ij k omega k, or we can write for the Lx, Ly and J, Lx will be equal to I double x omega x plus I xy omega y plus I xz omega z. That is the tensor form we already discussed and written in the matrix form, that is written here. Izx omega x plus Izy omega y plus Izz omega z. And you can write the previous from the previous matrix form. Now the diagonal elements is equivalent to moment of inertia coefficients. Diagonal elements are Ixx, Iyy and Izz. So that is equal to miri square minus xi square, and Iyy is equal to miri square minus yi square, and Izz will be equal to miri square minus zi square. That are the moment of inertia coefficients. And off diagonal elements, all other than diagonal elements, this and this, ix y iyx is equal to ix ixy and iyx are the off diagonal values, and similarly ixz and izx is equal to minus mixi zi, and that is mixi yi, and in the last, that is the products of inertia, so that is iyz and the izy, that is equal to minus miyi zi. You can see from here that is the y and z involved in it. Now moving to the next, inertia tensor ijk summation convention. I particle label, jk Cartesian xy in 1 to 3. We're going to write in the summation convention Lj is equal to, that is the summation, that is the tensor form. Compact form ijk is equal to, that is the general form of ijk is equal to miri square del jk minus ri j rij square is written in the two component form. All of this is the notation of discrete system of particles. For all the system of particles, that is the general form to be written as continuous boundaries sum over particles. Uh, sum over particles will be integrated over volume. We define rho r, and that is equal to mass density at position vector r, as ijk will be equal to, from that definition, integral of v rho r volume into mass density at the position vector r, and that will be equal to the term ri square del jk minus xi xj xk, and that will be equal to dv mass density will be equal to this. So or ixx is equal to integral v rho r square minus x square into dv iyy is equal to integral v rho r into r square minus y square dv. That is the whole values of all the diagonal values, and this is the ixy iyx, that is equal to integral v rho r into r square minus xy dv. Izx and xz will be equal to this value, and iyz and yz will be equal to this value. These are the off diagonal values. Hopefully till here you have understood the terms how to be written as. You have to follow all the steps I'm telling you here. So moving to next. Since the body is rigid, all elements I, j, k are constant in time. Clearly, they do depend on the region of the coordinates. It means that any kind of tensor, inertia tensor, that will be constant for the rigid body. But clearly, we can say that it depends upon the origin of the coordinates. Different if taken about the center of mass or elsewhere. If the center of mass is taken or elsewhere, then the coordinate or regions will be different. Now we can summarize Lj is equal to ijk omega k in even more compact form, that is L equivalent to I omega, where I omega I omega I is equivalent to inertia matrix. That I is the inertia matrix for the whole rigid body. And you know that a rigid body can be a spherical body. This is in the form of the orthogonal transformation. It means in the three-dimensional coordinate system. Clearly, it is and perpendicular to each other. Clearly, it is needed to take the interpretation that I acts on the vector omega, I acts on the vector omega to produce L, rather than the interpretation of I acting on the coordinate system.
इनर्शिया टेंसर एग्ज़ाम में काफ़ी इम्पोर्टेंट रहता है, काफ़ी बार आ जाता है एमएससी फिजिक्स में। सो इसे स्टार्ट करते हैं। सबसे पहले हम वी कंसिडर रिजिड बॉडी एज वन कंसिस्टिंग ऑफ डिस्क्रीट एंड सेपरेट पार्टिकल। हम रिजिड बॉडी कंसिडर करेंगे जो डिस्क्रीट होगी और सेपरेट पार्टिकल। बट इन रियलिटी वी नो जो हमारी रिजिड बॉडी होती है वो कंटिन्यूस होती है। ओके, सो रियलिटी से ये डिफरेंट है। अगेन डेंसिटी रो मैन नोट बी कांस्टेंट ओवर द इंटायर बॉडी। जो डेंसिटी रो है वो कांस्टेंट नहीं होती है। सो हियर मोर प्रॉपर ये रहेगा कि हम समेशन को इंटीग्रेशन में चेंज कर दें। कहाँ पर? इन दैट केस ऑफ मूवमेंट ऑफ इनर्शिया एंड प्रोडक्ट ऑफ इनर्शिया। ये पिछली वीडियोज़ में हम डिस्कस कर चुके हैं। यहाँ पर हम समेशन को किस में करेंगे? इंटीग्रेशन में करेंगे। इंटीग्रेशन वी ले लेंगे, डी वी ले लेंगे। पिछली वीडियोज़ में हमने यहाँ पर सिर्फ एक सिंगल पार्टिकल के किया था। यहाँ पर पूरा हम ले रहे हैं, एक रिजिड बॉडी ले रहे हैं। सो यहाँ पर एम आई की जगह ये वी कर दिया, रो कर दिया है। और इंटीग्रेशन वी डी वी आई एक्स एक्स ये आप सारे देख सकते हैं फॉर्मूले। आर माइनस एक्स स्क्वायर, वाई वाई जो सेम होंगे आर स्क्वायर, ये देख लीजिए। सो विद अ स्लाइड चेंज ऑफ इन सब में स्लाइड चेंज इन नोटेशन, ऑल 9 कोएफिशिएंट can be combined into a single one. Okay, as the coordinate axis can be denoted by x, कुछ इस तरह से हम दिखा सकते हैं। कॉम्पैक्ट फॉर्म उसकी इस तरह से होती है, आई जे के रो एक्स आर स्क्वायर क्रोनिकल डेल्टा जे के एक्स से एक्स के। यहाँ पर जैसे x1 आएगा तो आप x मान सकते हैं, x2 आएगा तो y मान सकते हैं, x3 आएगा तो z मान सकते हैं। सो आप एक एक करके यहाँ पर सारी क्वांटिटी रखिए। अगर ये दो क्रोनिकल डेल्टा की प्रॉपर्टी आप जानते होंगे। अगर वन वन सेम आएंगे तो ये क्या होगा? वन होगा। अगर डिफरेंट आएंगे तो ये वन टू, तो ये जीरो हो जाएगा। ये आप जानते होंगे। अगर यहाँ पर वन वन आएगा तो ये वन हो जाएगा। आर स्क्वायर माइनस एक्स स्क्वायर इस तरह से होगा। नहीं तो बाकी आप ये प्रॉपर्टी जानते होंगे। अगर सेम सेम आएंगे, वन आएगा क्रोनिकल डेल्टा की। So, where delta jk is chronicle delta symbol, it is obvious from the expression for angular momentum. The components of L are linear function. जो component होते हैं L के linear function होते हैं of omega, which may write in matrix. So हम कुछ मैट्रिक्स फॉर्म में L इज इक्वल टू आई ओमेगा देते हैं। सो हम मैट्रिक्स में कुछ इस तरह से लिख सकते हैं L1 L2 L3 I1 I12। सो ये मैट्रिक्स फॉर्म है इसका। सो इक्वेशन नंबर 2 देते हैं यहाँ पर हमारी, इसे इक्वेशन नंबर 1 दे देते हैं। इक्वेशन नंबर 1 एंड इक्वेशन नंबर 2, ये हमारी दो इक्वेशन आ गई है। द 9 एलिमेंट्स I11 I12 ये मैट्रिक्स फॉर्म में आ गए। 3 × 3 मैट्रिक्स फॉर्म में आ गए हैं। मे बी कंसिडर द कंपोनेंट्स ऑफ सिंगल एंटिटी आई, सिंगल एंटिटी आई की उसमें कर सकते हैं कॉल्ड अ टेंसर। एक टेंसर है ये। as the products of inertia satisfy the symmetry। कुछ प्रोडक्ट ऑफ इनर्शिया है जो सेटिस्फाई कर रही है सिमेट्रिक भी। सो ये जो प्रोडक्ट ऑफ इनर्शिया है सिमेट्रिक रिलेशन को कर रही होगी। मैं मान के चल रहा हूँ कि आप टेंसर को जानते होंगे। मैं फिर भी थोड़ा सा आइडिया देता हूँ। जैसे ये ए है, कोई टेंसर है ए बी इज इक्वल टू ए बी ए होगा कब? सिमेट्रिक पोजिशन में। ए बी माइनस ए बी ए होगा कब? जब इसको सिमेट्रिक होगा। ये सिमेट्रिक की कंडीशन है, ये इसको सिमेट्रिक। सो ये I11 I21 एंड I23 एंड I32 इस तरह से ये सिमेट्रिक। आई एक और है I13 I31। सो ये सिमेट्रिक दिखा रहे हैं। द टेंसर आई इज सिमेट्रिक टेंसर। नाउ द रिलेशन कनेक्टिंग कंपोनेंट ऑफ एल एंड ओमेगा कैन बी रिटर्न एज, सो हम इसे इस तरह से दिखा सकते हैं L इज इक्वल टू आई ओमेगा से। क्वेश्चन नंबर 3 देते हैं। वेयर द क्वांटिटी आई इज अ सेकेंड रैंक टेंसर। टेंसर को कैसे देखते हैं, ये एक रैंक का टेंसर है, ये टू रैंक का टेंसर है। इंडिसेस के हिसाब से हम देखते हैं कि सेकेंड रैंक का टेंसर है, एंड इज यूजुअली कॉल्ड द मोमेंट ऑफ इनर्शिया टेंसर। मोमेंट ऑफ इनर्शिया टेंसर कहते हैं, और ब्रीफली इसे हम इनर्शिया टेंसर इसी को कहते हैं। वी मे कंक्लूड दैट द प्रोडक्ट ऑफ इनर्शिया, the product of tensor I and vector ओमेगा इज अ वेक्टर। बहुत इंपॉर्टेंट लाइन है। जो हमारा प्रोडक्ट होगा टेंसर और वेक्टर का, टेंसर और वेक्टर का जो हमारा प्रोडक्ट होगा वो ऑल्सो वेक्टर होगा। अ, ठीक है, इसके अब अगले पार्ट में चलते हैं। सो इन डायरेक्ट नोटेशन में हम इस तरह से लिख सकते हैं, मोमेंट ऑफ इनर्शिया एम आई इज इक्वल टू आर आई स्क्वायर इंटू वन माइनस आर आई डॉट आर आई। डायरेक्ट नोटेशन क्या होता है, डायरेक्ट मीन्स सिंपल होता है कि एक सेकेंड रैंक टेंसर होगा, डायरेक्ट या डायरेक्ट टेंसर सेकेंड रैंक टेंसर होगा। सो हम दोनों साइड ओमेगा से मल्टीप्लाई कर देते हैं, आई ओमेगा। आई ओमेगा मतलब एल हो गया। सो आप देख सकते हैं इसको भी ओमेगा से, और यहाँ पर जो ये वन था ये हमारा यूनिट डायरेक्ट था। सो बाकी हमने ओमेगा से इसे मल्टीप्लाई कर दिया, एल आ गया। इन टर्म्स ऑफ इनर्शिया टेंसर द काइनेटिक एनर्जी को हम किस तरह से दिखा सकते हैं, टी इज इक्वल टू ओमेगा बार आई ओमेगा, ओमेगा स्क्वायर होता है, मतलब आप उसमें देख सकते हैं। सो यहाँ पर ओमेगा बार क्या है, ट्रांसपोज ऑफ कॉलम मैट्रिक्स ओमेगा। सो इसका ये ट्रांसपोज होगा। सो हम इसे एक्सपेंडेड फॉर्म में लिखते हैं, टी इज इक्वल टू वन बाई टू ट्रांसपोज कर लेते हैं इसका, और आई को भी मैट्रिक्स फॉर्म में और ओमेगा को इस फॉर्म में, ये ट्रांसपोज एक दूसरे के। सो कॉम्पैक्ट फॉर्म इसका यही होता है। सो वेयर टी इज स्केलर, ये टी इज स्केलर है। सो यहाँ से हम क्या निकाल सकते हैं, द मोमेंट ऑफ इनर्शिया अबाउट द एक्सिस ऑफ रोटेशन, मोमेंट ऑफ इनर्शिया अबाउट द एक्सिस ऑफ रोटेशन। सो यहाँ से हम कह सकते हैं कि प्रोडक्ट ऑफ टू वेक्टर्स एंड अ टेंसर, ये इसमें दो हैं, एक ओमेगा एंड ओमेगा बार, ये दोनों वेक्टर हैं। प्रोडक्ट ऑफ टू वेक्टर्स एंड अ टेंसर आई इज स्केलर। पहले वाले में क्या कहा था, अगर एक वेक्टर होगा, एक वेक्टर होगा और एक स्केलर होगा, इन दोनों का मल्टीप्लाई करेंगे तो क्या आएगा, ये आएगा नहीं, एक वेक्टर था एक टेंसर था, टेंसर हमारा आई था, तो ये क्या आएगा, वेक्टर आएगा। अगर दो वेक्टर होंगे और एक टेंसर होगा तो हमारा स्केलर आएगा। सो द वैल्यू ऑफ मोमेंट ऑफ इनर्शिया डिपेंड्स अपॉन द डायरेक्शन ऑफ एक्सिस ऑफ रोटेशन। ओके, इफ ओमेगा चेंजेस इट्स डायरेक्शन विथ रिस्पेक्ट टू टाइम, अगर ओमेगा चेंज करता है अपनी डायरेक्शन विथ रिस्पेक्ट टू टाइम, द मोमेंट ऑफ इनर्शिया मस्ट बी कंसिडर्ड इनटू अ फंक्शन ऑफ टाइम। सो मोमेंट ऑफ इनर्शिया क्या होगा, फंक्शन ऑफ टाइम होगा। The moment of inertia also depends upon the choice of the origin of a body set of axis. ओके, इस लेक्चर में इतना ही था, मिलते हैं किसी और लेक्चर में, थैंक यू।
Tensors, more pure math discussion, brief, hopefully a review. We're going to understand what are tensors. I is a tensor of second rank, and now a general discussion for that. We can say in Cartesian 3D space, we define a tensor of the nth rank, and capital T is equivalent to a quantity with 3 n power n elements or components t, I, j, k for the tensor, and n indices which transform under a orthogonal transformation of coordinates as coordinates a as summation convention. So we can write for that t prime I j k tensor into x prime is equal to a I L a j m a k n approaches to t l m n, and that is the equation x. Then factors of matrix element aij of capital M, that is all the a components of the metric elements of the matrix A. Aij is the elements of the matrix A. Tensor of zeroth rank is one element, that is scalar invariant in the orthogonal transformation capital A. Tensor of first rank is three elements that equivalent to ordinary vector transform under orthogonal transformation capital A as ti prime x prime is equal to aij tj x, and the tensor of second rank that have the 9 elements transform under the orthogonal transformation capital A like this. Rigorously, we have a distinction between the second rank tensor capital T and the square matrix formed from the elements of tensor, defined only by its transform properties under the orthogonal transforms. A matrix is a representation of a tensor in a particular coordinate system. Now, the relation between the inertia and the tensor, inertia tensor and the moment of inertia, as inertia is the second rank tensor transforms as such under the orthogonal transformation of the A. The angular momentum of a rigid body L is equal to I omega should more properly be written as L is equal to I a thick dot into omega, and that thick dot is written for the matrix multiplication or the matrix or the tensor multiplication. As here inertia is not a simple inertia, it is inertia of a body of a system of a rigid body, and it is in the tensor form in three-dimensional coordinate or the orthogonal components. Now we'll derive a form from the kinetic energy capital T for a rigid body in terms of I and omega. As I works on the omega, start with the kinetic energy of motion about a point in the form that is capital T equivalent to 1 over 2 mivi square. That will become 1 over 2 mivi, that the tensor form product multiplication vi. Rigid body is the only contribution to vi is from body rotation. uh, as before used vi dr as we before use vi is equal to dri over dt, and that will be equal to dr over dri over dt into r and plus omega cross ri, and that is equal to 0 plus omega into omega cross ri. Convenient to use with only one of the vi in the dot product. We are going to write the vector triple product for that. So t is equal to 1 over 2 mi vi dot into v omega cross ri. Permitting the vectors in triple product form, we're going to write a vector triple product here. So the capital T is equal to 1 over 2 omega dot into mi into ri cross vi, and from multiplication of the mi inside we get 1 over 2 omega into L, that R cross B gives the L value. Now using L is equal to I dot omega, this becomes T is equal to 1 over 2 omega dot I dot omega, and that becomes capital note order matters, and product with omega when thick dot is to left of I and the right of the I is clearly different. The dot on the left is have a different meaning, and that dot on the right have a different meaning. Capital T is clearly a scalar as it should be. Often I may write it simply capital T is equal to 1 by 2 omega I, and leaving out that dot, uh, and both of these have the different meanings. Now moving to the next, we're going to discuss is that this is the kinetic energy giving that equation 1, and is the unit vector along the rotation axis. So we that we can write omega is equal to omega n unit vector. Omega is a vector quantity, so written in the unit form. Then equation 1 can be written as t is equal to 1 by 2 omega square, and the vector products are not multipliable, so we wrote its magnitude. So magnitudes are multipliable, so there that is written omega square n unit vector dot I, that is the tensor form dot n unit vector, that gives unit vector is equal to 1, so that is 1 by 2 omega squared in the equation number 2. Here capital I is equivalent to unit vector tensor inertia tensor dot n unit vector, that is the moment of inertia about the rotation axis. So on the place of that we have write the I. Using forms of I from before, we can write that equation I is equal to n dot I dot n, and from previous we can write for this mi square m into ri square minus ri dot n unit vector whole square, that is the equation number 3. From definition 3 of I is consistent with the elementary of definition as sum over all the particles of the product, that whole value of particle mass times squares of the perpendicular distance from the rotational axis, and that is I is equal to mi into ri square. That is the perpendicular distance for the perpendicular distance of inertia. uh, Moving to the next, that is the kinetic energy. That is the moment of inertia we have already calculated. Clearly, moment of inertia depends on the direction n of the rotation axis. Also, for a rigid body in motion, the direction and thus the direction of omega can be time dependent. In general, I is equal to it. In the important special case where the body is constrained to rotate about a fixed axis, clearly then I is equal to constant. Special case when the body is constrained at a fixed point, so the inertia will be constant. When this is the case, then the kinetic energy in the form of equation 1 can be used in the Lagrange formulations. If inertia is constant, then this equation from the equation 1, the kinetic energy is used, worked out by the Lagrange formulation. If we can write omega as the time derivatives of some angle. That is the moment of inertia about axis, as you can see in the figure. Inertia tensor I double dot and moment of inertia I depend on the choice of the body axis origin. However, the moment of inertia about a given axis is simply related to the moment of inertia about the parallel axis through the center of mass. Parallel axis theorem. So from the figure 2, parallel rotational axis A and B uh, and direction n, axis B passes through the center of mass, and capital capital R and Ri is equal to position of center of mass, and the particle ith with respect to the origin O that have the position vector Ri. Position of the particle I with the respect to center of mass is Ri is equal to Ri prime, that is equal to Ri prime is equal to R plus Ri prime, that will be equal to Ri minus capital R, or you can say Ri is equal to R plus Ri prime. Moment of inertia about the axis A will be written as Ia is equal to summation I mi Ri cross n unit vector square is equal to summation I mi into, substituting that value we have R plus R I prime cross into cross n whole unit vector into whole square, and that becomes summation I mi capital R cross n unit vector whole square plus summation I we're going to substitute the distributive, we're going to open the square, so we're going to write the A term and B term. So we write A term plus MIRI cross n square plus 2. And one term is with that and second term is with that. So plus 2 summation I M I R cross n unit dot R I prime cross n unit vector. Now, moment of inertia about axis A, that is written as like this. Moment of inertia about axis B will be written similarly in like this. Note that summation I MIR cross n square equivalent to MR cross n unit whole square. That summation IMI is converted into capital M whole mass of the rigid body. So IA is equal to IB plus M in capital M into R cross R vector cross n unit vector whole square plus 2 summation IMI R cross n dot RI prime cross n unit vector. Rewrite the equation. Rewrite third term as first term, second term, and third term as 2R cross 2 into R cross n unit dot expression IMI R prime cross n. Note that by definition of center of mass, that will set center of mass, all the moment will be the momentum will be zero. So the term 2 summation IMI R cross n unit vector dot Ri prime cross n is equal to 0. So all the whole term will be equal to 0. So we are left with the Ia is equal to Ib plus capital M into R vector cross n unit vector whole square for theta, that is equal to angle between the capital R and the rotational axis and perpendicular distance between the axis A and B. is equal to r cross n unit vector is equal to r sin theta is equal to r perpendicular, that is equal to ia is equal to ib plus mr square sin square theta. That is called the parallel axis theorem. So we can write ia is equal to ib plus capital M into r perpendicular whole power square, that is the perpendicular distance between the two parallel axes. This is the final equation. In words, we can write the definition. The moment of inertia about an arbitrary axis is equal to the moment of inertia. Moment of an arbitrary axis is equal to the moment of inertia about a parallel axis passing through the center of mass, or as shown in the figure, plus the moment of inertia of the body about the arbitrary axis, any axis, taken as if all the mass or all of the mass, capital M of the body, were at the center of the mass.
What's a tensor? I love this illustration by Carl Stratos, who's a professor at Rutgers specializing in natural language processing. Tensors are objects in linear algebra, just like vectors and matrices. It helps to think about what type of data we have and how we choose to represent them. If our data is one-dimensional, we express it using a single number. This is a scalar. When we have n-dimensional data, we represent these as a list of numbers, which we call a vector. One thing you'll often see in tensor algebra and calculus is index notation. Vi is the ith component of the vector v, where v has components ranging from v1, v2, etc. through vn. Many linear algebra notions are simplified using what's called the Einstein summation convention. In this convention, repeated indices are summed over. For instance, q dot r can be written as the sum on I of qi times ri, or in Einstein notation, this is simply written as qi times ri, where the summation is implicit. You'll often see this as raised and lowered indices in other subjects, such as general relativity, where you need to pay attention to covariant and contravariant vectors. This is like thinking of the dot product as the result of multiplying a row vector by a column vector. So in this version of the summation convention, only pairs of repeated indices with one raised index and one lowered index are summed over. In Euclidean space, these dual spaces are isomorphic, so we can ignore the raising and lowering operations. Matrices and tensors are ways of representing multilinear data. These are given by arrays of numbers. A matrix is the simplest form of a tensor. We can see this in the eigensystem equation, mv equals lambda v. We can write this in summation notation as mij times vj is equal to lambda times vi. So the ijth component of the matrix M is multiplied by the jth component of the vector v, and this is equal to the scalar lambda times the ith component of the vector v. The number of i's and j's in the system depends on the overall dimensionality of the system, not on the number of dimensions of the array. Many tensors aren't represented by two-dimensional arrays. The rank of a tensor is the number of indices it has. From this point of view, a scalar is a rank 0 tensor. A vector is a rank 1 tensor. A matrix is a rank 2 tensor, since it has ij. The first tensor of rank greater than 2 you're likely to encounter comes in the definition of the cross product. So let's consider the cross product S is equal to Q cross R. The ith component of S is equal to epsilon ijk times qj times rk, where epsilon is the totally antisymmetric tensor that is equal to 1 when ijk is an even permutation of 1, 2, 3, and minus 1 when ijk is an odd permutation of 1, 2, 3, and 0 in all other cases. In my research, we end up dealing with the rank 4 elastic constant tensor. This is Cijkl. General relativity has a rank 4 Ricci curvature tensor. However, in this video, we'll be primarily dealing with a rank 2 tensor, and that is the moment of inertia tensor, Iij. Here we have an object that's rotating through an axis that's anchored to the origin of our lab frame. It has infinitesimal mass element dm located a distance r from the origin. It has angular momentum dl is equal to the radius r cross the momentum of the mass element, where the momentum of the mass element is given by its velocity times its infinitesimal mass, which is given by omega cross r. Then the total angular momentum in our system is the integral of r cross the infinitesimal momentum, which is omega cross r times dm. What we're going to do is expand out these cross products to derive the form of the moment of inertia tensor. First, let's look at the term omega cross r. We can calculate the cross products using the determinant of a matrix consisting of the unit vectors in the Cartesian basis, the components of the first vector, and lastly the components of the second vector. And this gives us omega y times z minus omega z times y in the x hat direction plus omega z times x minus omega x times z in the y direction plus omega x times y minus omega y times x in the z direction. But for now, we're going to write this as components of the velocity of our mass element for space reasons. Now that we know what omega cross r is as a vector, we can calculate the full vector of r cross omega cross r. So this is given by the determinant of a matrix composed of the unit vectors, the components of the r vector, and the components of the v vector. This gives us omega x times y squared plus z squared minus omega y times xy plus omega z times xz in the x direction, plus omega y times x squared plus z squared minus omega x times xy plus omega z times yz in the y direction, plus omega z times x squared plus y squared minus omega x times xz plus omega y times yz in the z hat direction. But we also know that the total angular momentum is given by I, so our moment of inertia tensor, times the vector omega. So let's collect the components that contain first omega x. These are omega x times y squared plus z squared in the x hat direction, minus omega x times xy in the y hat direction, and minus omega x times xz in the z hat direction. And likewise, we can collect all of the components that are multiplied by omega y and omega z. And when we factor out the omega x's, omega y's, and omega z's, we're left with a rank 2 tensor that has all of the components of our moments of inertia. Thus, our full moment of inertia tensor is given by the integral of y squared plus z squared dm minus the integral of xy dm minus the integral of xz dm minus the integral of yx dm, the integral of x squared plus z squared dm, minus the integral of yz dm, minus the integral of zx dm, minus the integral of zy dm, the integral of x squared plus y squared dm. This is a lot of algebra all at once, but let's decompose the components and see what's going on. First, we'll look at the diagonal components. So each of these has a component that measures the distance squared of the infinitesimal mass element from each of the Cartesian axes. So the xx term here integrates the distance to the x-axis of our infinitesimal mass element in the yz plane, and its distance is y squared plus z squared. The yy component measures the distance to the y-axis, so that's this distance here, and this is measured in the xz plane. And lastly, the zz component measures the distance from the mass element to the z-axis, and that's measured in the xy plane. The off-diagonal terms measure the distance from the infinitesimal mass element to the lines x equals y, x equals z, and y equals z. Notice that since x equals y implies also that y is equal to x, the moment of inertia tensor is symmetric. Now that we know the moment of inertia tensor for this body rotating about an arbitrary axis anchored at the origin, what is the kinetic energy of this body? We'll start with the kinetic energy of the infinitesimal mass element dm. This element has kinetic energy given by 1/2 dm times its velocity squared. This is 1/2 times dm times the magnitude of the vector omega cross r squared. Then the total energy is obtained by integrating this infinitesimal kinetic energy across the whole body. From the components of the vector omega cross r, this is going to be given by 1/2 the integral on dm of omega y times z minus omega z times y quantity squared, plus omega x times z minus omega z times x quantity squared, plus omega x times y minus omega y times x quantity squared. Then if we do the same termwise analysis we just did, this shows that the kinetic energy is equal to 1/2 the row vector omega x, omega y, omega z times the moment of inertia tensor I times the column vector omega x times omega y times omega z. And we can write this as 1/2 omega transpose, so this takes the omega, which we normally write as a column vector, and turns it into a row vector, times the moment of inertia tensor times the regular column vector version of our angular velocity. Or equivalently, this is written as 1/2 the angular velocity vector dotted into the angular momentum, which is I times omega. What if our object is both translating and rotating? Imagine now that our object is translating at some velocity vcm while rotating about some axis omega, which is no longer anchored to the origin. Then the center of mass is located at rcm, and the distance from the center of mass to an infinitesimal mass element we're going to call r prime. Our definition v equals omega cross r doesn't hold anymore. That was only valid for rotations where the axis of rotation is anchored at the origin. So let's rearrange our system so we can take advantage of this particular convenient substitution. From Chazzel's theorem, we know that all motion can be decomposed as the sum of a translational velocity and a rotational velocity. So here the translational velocity is vcm, and the rotational velocity is v prime. Since the axis of rotation passes through rcm, we can now use that in the simplification. So we find that v prime is equal to omega cross r prime, where r prime is this distance here. Since the axis of rotation is passing through rcm, we can now use the simplification that v prime is equal to omega cross r prime. So the velocity of our mass element is now given by vcm plus omega cross r prime. This definition lets us extend the total angular momentum, or the integral of r cross v times dm, as the integral of rcm plus r prime cross vcm plus omega cross r prime, and we're integrating that over dm. When we group terms, we get rcm cross vcm times the total mass plus the integral of r prime cross omega cross r prime integrated over dm. This term here is the angular momentum that we just derived for our object rotating about an arbitrary axis that's fixed to the origin. So again, we discover the familiar decomposition that the angular momentum can be written as an orbital component plus a spin component. Likewise, the kinetic energy, which is 1/2 times the integral of v squared dm, is now equal to 1/2 vcm plus omega cross r quantity squared dm. And again, we can break this into two components. So the first is 1/2 m times vcm squared, and the other is 1/2 omega dotted into the angular momentum about the center of mass. Therefore, the kinetic energy is also the sum of a translational component and a rotational component. When we're actually solving problems, we don't want to have to worry about keeping the axis of rotation passing either through the origin or its center of mass. Doing integrals for the moment of inertia tensor in these coordinates is messy, and if the axis of rotation changes, the algebra can get even worse. So instead, what we do is construct a coordinate system that's based on the body of the object we're studying. To do this, we're going to change our basis so that the moment of inertia tensor is diagonal. So in this new basis, our moment of inertia tensor looks really nice. It just has components I11, I22, and I33 all down the diagonal. These are known as the principal moments. They're also the eigenvalues of the moment of inertia tensor. The new basis is given by the unit vectors omega hat, which are called the principal axes. And these are the eigenvectors of the moment of inertia tensor. In this new coordinate system that's stuck to the body of the object, the angular momentum is given by I11 times omega 1, I22 times omega 2, and I33 times omega 3. Likewise, the kinetic energy is also quite simple. It's given by 1/2 I11 times omega 1 squared plus I22 times omega 2 squared plus I33 times omega 3 squared. There are some cases where this can be even further simplified. Usually this means that there's a symmetry of the system that we can take advantage of. That means that there's some degenerate subspace in this moment of inertia tensor. For instance, if two moments are the same, then any axis passing through the origin in the plane of those two principal axes is also a principal axis. An example of this is this yield sign, which has in-plane rotational symmetry that isn't 180 degrees. Then any axis in this xy plane can be considered a principal axis, and all of them will have the same moment.
That is the end of the topic. So we are going to uh, discuss that topic, if any kind of difficulty, in the next physical class. So hopefully the topic was easy to understand. If there is any kind of difficulty, we will discuss in the class next. Thank you so much. And these are the references for you to get help from for your lecture for the classical mechanics. Thank you so much. Allah Hafiz.